Right now, inside every atom of your body, something impossible is happening. Protons, particles that carry positive electrical charge, are packed together in a space so small that 100,000 nuclei laid side by side wouldn't span the width of a single atom. And positive charges repel each other, violently. The closer they get, the harder they push apart. At the distances inside a nucleus, the electromagnetic repulsion between just two protons is roughly 50 pounds of force, enough to launch a grain of sand across a room. Multiply that by dozens of protons crammed together, and the nucleus should detonate the instant it forms. It should be the most unstable structure in nature. And yet, it holds. The atoms in your bones, in the iron core of the Earth, in the heart of every star, they all hold together. Something is overpowering that repulsion, and what it is will change how you see matter itself. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Pick up anything: a coin, a glass of water, your phone. Hold it in your hand and feel its weight. It feels solid, continuous, like it is one unbroken piece of stuff. You press your thumb against it and it pushes back. It has edges and surfaces and mass. Everything about the experience tells you this object is real in a straightforward, uncomplicated way. Solid matter doing solid things. But that experience is a lie. Not a small lie, a spectacular one. Because the thing you are holding is almost entirely empty space. Every atom that makes up that object, every atom that makes up you, is overwhelmingly nothing. And all the mass you feel, all the resistance, all the weight, nearly all of it comes from a structure so small you could never see it, no matter how powerful your microscope. A structure so tiny that the only reason we know it exists at all is because of a bizarre experimental result over a century ago that made absolutely no sense at the time. That structure is the atomic nucleus, and it is one of the strangest objects in the known universe. Let us start with what an atom actually looks like, because the picture most people carry in their heads is wrong. You have probably seen diagrams in textbooks showing a cluster of balls in the center with little round electrons tracing neat circular paths around them, like planets orbiting a star. Those diagrams are useful for getting the basic idea across, but they are deeply misleading in one crucial way. They get the scale completely wrong. In those diagrams, the nucleus takes up maybe a fifth or a tenth of the atom. It looks like a reasonably large core surrounded by electrons at modest distances. The reality is nothing like that. An atom is about 1/10 of a nanometer across. A nanometer is 1/1000th of a meter, so an atom is roughly 1/10 billionth of a meter in diameter. That is already absurdly small. You could line up roughly 1,000,000 atoms across the width of a human hair. But the nucleus sitting at the center of that atom is far, far smaller than the atom itself. The nucleus is about 1 femtometer to a few femtometers across. A femtometer is 1/quadrillionth of a meter, 1/1,000,000th of a nanometer. The nucleus is roughly 100,000 times smaller than the atom it sits inside. Think about what that means. If you could blow an atom up to the size of a major sports stadium, say a football field with all the seating around it, the nucleus would be a small marble sitting on the 50-yard line, maybe a blueberry. Everything else, the entire vast volume of that stadium, would be empty, not filled with anything, not containing some kind of atomic substance, just empty space with a few electrons somewhere in the upper decks, each one far too small to see even at this scale. The atom is a cathedral of nothing, with a speck of something at the center. And here is the astonishing part. That tiny speck, that marble on the 50-yard line, contains 99.96% of the atom's entire mass. Almost everything the atom weighs is concentrated in that minuscule central dot. The electrons buzzing around contribute almost nothing to the mass. If an atom were a person weighing 170 pounds, the electrons would weigh about 1.5 ounces. Everything else, the bones, the muscle, the organs, everything, would be the nucleus. This means the nucleus is unimaginably dense. You are packing nearly all the mass of the atom into a volume that is 1,000,000 billion times smaller than the atom. If you could somehow collect a cubic centimetre of pure nuclear material, about the size of a sugar cube, it would weigh roughly 230 million metric tons. That is more than the mass of every building in a major city combined, crushed into a space you could hold between your fingers. Nuclear matter is the densest stable form of matter in the ordinary universe. Nothing you will encounter in daily life comes remotely close. Not the densest metals, not the core of the Earth, nothing. So how did we discover this absurd structure? How did we figure out that atoms have these incredibly tiny, incredibly dense cores? The answer involves one of the most important experiments in the history of physics. And it starts with a man who was already famous for taking atoms apart. In the early 1900s, the prevailing model of the atom was something called the plum pudding model, proposed by J.J. Thomson. Thomson had discovered the electron in 1897, proving that atoms contained negatively charged particles. He proposed that an atom was a sphere of uniformly distributed positive charge, with electrons embedded inside it, like raisins in a pudding. The positive charge was spread out evenly through the whole volume of the atom, and the electrons sat within that positive cloud, held in place by electrical attraction. In this model, there was no nucleus, no dense central core, just a diffuse blob of positive charge filling the entire atom, with electrons scattered through it. This model made sense at the time. If positive charge was smoothly distributed throughout the atom would be electrically neutral overall, which matched observations. The electrons could vibrate within the cloud, potentially explaining how atoms absorb and emit light. It was a reasonable hypothesis, given what physicists knew. But it was wrong. Ernest Rutherford, a New Zealand-born physicist working at the University of Manchester, designed an experiment to test the plum pudding model. He worked with Hans Geiger and Ernest Marsden. Their approach was elegant. Fire small, fast-moving projectiles at atoms and see what happens. The projectiles were alpha particles, which are essentially helium nuclei. 2 protons and 2 neutrons bound together, carrying a positive charge and moving at roughly 5% of the speed of light. Rutherford's team fired these alpha particles at a very thin sheet of gold foil, only a few hundred atoms thick. If the plum pudding model was correct, the alpha particles should pass through the gold foil with only slight deflections. Positive charge spread evenly through the atom would not create strong enough electric fields to significantly deflect a fast-moving alpha particle. It would be like rolling a bowling ball through a cloud of mist. The ball might slow down slightly, might wobble a tiny bit, but it would punch straight through. The mist does not have the concentrated mass or charge to stop it. And that is exactly what happened. Most of the time, the vast majority of alpha particles sailed straight through the gold foil as if it were not there. This was consistent with the plum pudding model. But then Geiger and Marsden noticed something that was not consistent at all. A small number of alpha particles, roughly 1 in 8,000, bounced back at large angles. Some came back almost directly toward the source, deflected by more than 90 degrees. A few bounced almost straight back the way they came. Rutherford was stunned. He later described his reaction by saying it was as if you had fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. In the plum pudding model, this was impossible. A diffuse cloud of positive charge could not create a strong enough electric field to reverse the direction of a fast alpha particle. For that to happen, the positive charge had to be concentrated in an extremely small, extremely dense region. The alpha particle had to be getting close to something with enormous charge density, something that could generate a powerful enough repulsive force to send it flying backward. Rutherford worked through the mathematics. He calculated that if all the positive charge and nearly all the mass of a gold atom were packed into a region smaller than about 10 femtometers across, the resulting electric field would be strong enough to deflect alpha particles at exactly the angles they observed. The numbers matched perfectly. The atom was not a pudding. It was almost entirely empty space with a tiny, dense, positively charged core. Rutherford announced his nuclear model of the atom in 1911, and it changed physics forever. This was a profound moment. The discovery of the nucleus did not just tell us something new about atoms. It revealed that the matter making up everything around us, everything we touch and see and feel, is structured in a way nobody had imagined. Almost all the mass is concentrated in objects so small they dwarf even the tiny scale of atoms. The solid world is an illusion created by electromagnetic forces between atoms. The actual material substance, the mass, is locked away in specks so minute they seem almost theoretical. Now, once Rutherford discovered the nucleus, the next question was obvious. What is it made of? Rutherford already knew the nucleus carried positive charge. He knew each element had a different amount of positive charge in its nucleus. Hydrogen, the lightest element, had 1 unit of positive charge. Helium had 2. Carbon had 6. Gold had 79. So the nucleus contained positively charged particles. These particles were named protons. Each proton carries exactly 1 unit of positive electric charge, equal in magnitude but opposite in sign to the charge of an electron. A hydrogen nucleus is just a single proton. A helium nucleus has 2 protons. An oxygen nucleus has 8. A uranium nucleus has 92. The number of protons defines which element an atom is. Change the number of protons and you change the element entirely. But protons alone could not explain the nucleus. There was a mass problem. A helium nucleus has 2 protons, but it weighs 4 times as much as a hydrogen nucleus, not twice. A carbon nucleus has 6 protons, but weighs 12 times as much as hydrogen, not 6 times. Across the periodic table, nuclei were consistently heavier than their proton count could explain. Something else was in there, adding mass without adding positive charge. In 1932, James Chadwick solved the puzzle. He discovered the neutron, a particle with almost the same mass as a proton, but no electric charge at all. Neutrons are electrically neutral. They sit in the nucleus alongside protons, contributing mass and, as we will explore, playing a critical role in holding the nucleus together. With this discovery, the picture of the nucleus became clear. The nucleus is made of protons and neutrons, collectively known as nucleons. Protons carry positive charge, neutrons carry none. Together, they account for nearly all the mass of every atom. A hydrogen nucleus is the simplest. 1 proton, nothing else. A helium nucleus has 2 protons and 2 neutrons, 4 nucleons total. Carbon has 6 protons and 6 neutrons. Iron has 26 protons and 30 neutrons. Uranium, one of the heaviest naturally occurring elements, has 92 protons and 146 neutrons. 238 nucleons, crammed together in a space just a few femtometers across. Stop and think about what that actually means physically. 238 nucleons inside a uranium nucleus. Each nucleon is itself about 1 femtometer across, and the entire nucleus is only about 15 femtometers in diameter. These particles are not floating around with comfortable space between them. They are pressed together, shoulder to shoulder, almost touching, separated by distances comparable to their own size. Imagine packing 238 tennis balls into a container that is only 15 tennis balls wide. There is almost no room. Every nucleon is in physical contact with multiple neighbors. There is no empty space to spare, no gaps, no breathing room. The nucleus is not like an atom, which is almost entirely void. The nucleus is full. It is packed to capacity. It is one of the most crowded environments in the natural world, and every single one of those nucleons is moving. They are not sitting still. Quantum mechanics forbids it. The uncertainty principle guarantees that a particle confined to such a tiny space must have substantial kinetic energy. Nucleons inside the nucleus are whipping around at speeds of roughly 60,000 kilometers per second. That is about 20% of the speed of light. Inside a space smaller than a trillionth of a millimeter, particles nearly as heavy as a hydrogen atom are moving at a significant fraction of light speed, constantly colliding with their neighbors, bouncing off one another, held in by the collective pull of the surrounding nuclear material. The nucleus is not quiet. It is not calm. It is a frenzy of motion, a roiling storm of particles crammed into the smallest stable structure that ordinary matter can form. This is the environment in which the paradox plays out. Not in some abstract theoretical setting, in this tiny, heaving, impossibly dense knot of particles that sits at the heart of every atom you have ever encountered. And this is where the paradox becomes impossible to ignore, because every single one of those protons carries a positive electric charge, and positive charges repel each other. This is one of the most fundamental facts in all of physics. Like charges repel. It is called the electromagnetic force, and it is described precisely by Coulomb's law, which tells you exactly how strong the repulsion is between two charged particles at a given distance. The force is proportional to the product of the charges and inversely proportional to the square of the distance between them. That inverse square law is the key to understanding why the nucleus is so paradoxical. When you double the distance between two charges, the force drops to 1/4. But when you halve the distance, the force quadruples. And inside a nucleus, the distances are extraordinarily small. Protons inside a typical nucleus are separated by about 1 to 2 femtometers. At that distance, the electromagnetic repulsion between just two protons is enormous. Let us put actual numbers on this so you can feel how extreme it is. Two protons sitting 1 femtometer apart experience a repulsive force of about 230 newtons. That is roughly 52 pounds of force. Between two particles so small you could fit trillions of them on the head of a pin. 52 pounds of force pushing them apart. That is enough force to accelerate a small coin at thousands of times the acceleration of gravity. At nuclear distances, the electromagnetic force between protons is savage, and it gets worse as you add more protons. Every proton in the nucleus repels every other proton. The repulsion is not just between neighbors, it reaches across the entire nucleus, because the electromagnetic force has infinite range. It weakens with distance, but it never goes to zero. A proton on one side of a uranium nucleus is still being pushed by protons on the opposite side. Add up all the repulsive forces between 92 protons, and the total electromagnetic energy trying to blow the nucleus apart is staggering. For a uranium nucleus, the total electromagnetic repulsion energy is roughly 900 million electron volts. That is a tremendous amount of energy for something so small. To appreciate what this means, consider that the chemical reactions powering your body operate at energies of a few electron volts per atom. The repulsion energy inside a uranium nucleus is hundreds of millions of times larger than the energy of ordinary chemistry. The force trying to destroy the nucleus is not subtle. It is not marginal. It is overwhelming. So why does the nucleus not fly apart? This question haunted physicists for decades. After Rutherford discovered the nucleus, it became immediately obvious that electromagnetic forces alone could not explain its existence. Gravity was useless at this scale. The gravitational attraction between two protons is roughly 36 orders of magnitude weaker than their electromagnetic repulsion. That is a factor of 1 followed by 36 zeros. Gravity cannot hold the nucleus together, not even close. So there had to be another force. A force that nobody had identified yet. A force that operated only inside the nucleus, powerful enough to overwhelm the electromagnetic repulsion between protons and bind nucleons together despite their desperate electrical desire to fly apart. And this force had to have a very peculiar property. It had to be incredibly strong at very short distances, strong enough to overpower electromagnetism at the femtometer scale. But it also had to vanish almost entirely at larger distances, because we do not feel this force in everyday life. Atoms do not stick to each other because of nuclear forces. Molecules do not form because of whatever holds the nucleus together. This force had to turn on only when particles were extremely close, closer than a few femtometers, and turn off completely beyond that range. Nothing in classical physics predicted such a force. Electromagnetism reaches across the universe. Gravity reaches across the universe. Both weaken with distance, but neither has a hard cutoff. A force that is enormous at 1 femtometer and essentially zero at 10 femtometers was something entirely new. It did not fit into any existing framework. Understanding what this force is, how it works, and why it behaves so differently from anything physicists had seen before would require a revolution in physics. A revolution that would reveal hidden layers of reality inside the proton and neutron themselves. But before we go there, let us sit with the paradox a moment longer, because it is worth appreciating just how strange the nucleus really is. You are made of atoms, trillions upon trillions of them, and every single one of those atoms exists only because its nucleus holds together against overwhelming electromagnetic force trying to tear it apart. Every element heavier than hydrogen, every atom of carbon in your muscles, every atom of calcium in your bones, every atom of iron in your blood, exists because something inside that tiny femtometer scale core is winning a violent tug of war against one of the 4 fundamental forces of nature. If that something were even slightly weaker, nuclei beyond hydrogen would not exist. There would be no carbon, no oxygen, no iron, no complex chemistry, no molecules, no planets, no life. The universe would be a thin, cold soup of isolated protons and electrons with no possibility of the richness we see around us. Everything you know, everything you are, depends on the nucleus being stable. And the nucleus being stable depends on a force strong enough to defeat electricity at close range and precise enough to know when to stop. Consider the gold foil that Rutherford's team used. Gold has 79 protons in each nucleus, along with 118 neutrons. Every one of those 79 protons is repelling every other proton with tremendous force. The electromagnetic energy trying to blow apart a single gold nucleus is hundreds of millions of electron volts. And yet gold is one of the most stable elements in nature. Gold nuclei formed inside dying stars billions of years ago, survived the explosion that scattered them into space, drifted through interstellar clouds, got swept up into the formation of our solar system, sank into the molten Earth, and eventually got pushed to the surface by geological activity. Those nuclei have lasted for billions of years, sitting there calmly, 79 protons coexisting in a space smaller than anything you have ever imagined, as if the ferocious electrical repulsion between them were not even there. This is the object we need to explain, not a simple thing, not a featureless lump, not a smooth, static core. The nucleus is a dynamic, crowded, energetic system of individual particles held together by a force that most people have never heard of, resisting another force that should destroy it utterly. It is the most fundamental structure in the material world. Without it, matter as we know it could not exist. And understanding how it works requires us to go deeper than Rutherford could, deeper than protons and neutrons, into the strange and beautiful physics that governs the smallest scales in nature. The electromagnetic force does everything it can to tear the nucleus apart. And something else, something far more powerful and far more mysterious, holds it together. That something is what we need to understand next. Because it is not just strong. It is a shadow of the strongest force in the known universe. And it plays by rules that are unlike anything else in physics. So the nucleus should not exist. We established that. Every proton inside it is pushing against every other proton with tremendous electromagnetic force, and at the femtometer distances inside a nucleus, that repulsion is savage. Hundreds of millions of electron volts of energy trying to blow the whole thing apart. And yet, the nucleus holds. Something is overpowering electromagnetism at close range, and whatever it is must be extraordinary. Because electromagnetism is not a weak force. It is the force that holds atoms together, that creates chemical bonds, that makes lightning strike and magnets cling to your refrigerator. It governs nearly everything you experience in daily life. And inside the nucleus, something is beating it. Not by a small margin, by a landslide. That something is called the residual strong interaction. And it is the reason you exist. Let us talk about what this force is, how it works, and why it behaves so differently from anything else in physics. Because the residual strong interaction is strange. It does not follow the rules you might expect from your experience with electromagnetism or gravity. It operates in a completely different way, with completely different properties, and understanding those properties is the key to understanding why nuclei can form at all. The first thing to know is that the residual strong interaction is enormously powerful. At its effective range, roughly 1 to 2 femtometers, it is far stronger than the electromagnetic repulsion between protons. The attractive pull it creates between two neighboring nucleons is on the order of 10,000 newtons at peak strength. Compare that to the electromagnetic repulsion between two protons at the same distance, roughly 230 newtons. The strong attraction is dozens of times more powerful. Electromagnetism does not stand a chance in a head-to-head contest at nuclear distances. But here is the strange part. The residual strong interaction is incredibly short-ranged. This is what makes it so unusual and so different from the forces you are familiar with. Electromagnetism has infinite range. Two charged particles on opposite sides of the universe still exert a force on each other. It is tiny, vanishingly small at cosmic distances, but it never reaches zero. Gravity is the same way. Infinite range. Every mass in the universe attracts every other mass, no matter how far apart they are. The forces weaken with distance, but they never fully disappear. The residual strong interaction is nothing like that. It is powerful at 1 femtometer, still significant at 2 femtometers, and essentially gone by 3 femtometers. Beyond roughly 2.5 to 3 femtometers, the force drops so steeply that it might as well not exist. It does not gradually fade like electromagnetism, it falls off exponentially, which means it plummets towards zero far faster than any inverse square law. At 5 femtometers, it is negligible. At 10 femtometers, it is completely undetectable. The force that holds the nucleus together cannot even reach across a single atom. This is why you never feel the nuclear force in everyday life. Your hand is made of atoms. Those atoms are separated by distances of roughly 1/10 of a nanometer, which is 100,000 femtometers. At that distance, the residual strong interaction has been dead for 100,000 times over. The nuclear force between atoms in your hand is exactly zero. It only operates when nucleons are practically touching. It is the ultimate short-range force. Now, this combination of extreme strength and extreme short range is not just a curiosity. It is the reason the nucleus has a well-defined size and shape. Think about what would happen if the nuclear force had infinite range like electromagnetism. If it was strong and long-ranged, every proton and neutron in the universe would attract every other proton and neutron. All matter would collapse into one enormous nuclear blob. There would be no separate atoms, no separate nuclei, just a single lump of nuclear material. The universe would look nothing like what we see. Conversely, if the nuclear force were long-ranged but weak, it would not be able to compete with electromagnetic repulsion. Nuclei with more than one proton would fly apart. Only hydrogen could exist. No heavy elements, no chemistry, no complexity. The fact that the force is both strong and short-ranged is what creates nuclei with specific sizes. Add nucleons to a nucleus and the nuclear force binds them tightly to their nearest neighbors. But the attraction does not reach across the entire nucleus. A proton on one side of a large nucleus feels strong attraction only from the nucleons right next to it, not from nucleons on the far side. Meanwhile, the electromagnetic repulsion, which does have infinite range, adds up across the whole nucleus. Every proton pushes against every other proton, regardless of distance. This is why very large nuclei become unstable. The strong force binds locally. The electromagnetic force repels globally. Beyond a certain size, the global repulsion wins, and the nucleus can no longer hold together permanently. But we are getting ahead of ourselves. Let us understand where this force comes from. In the 1930s, physicists were desperate to explain what held the nucleus together. They knew it was not electromagnetism. They knew it was not gravity. They needed a new force, and they needed a theory that could describe it. In 1935, a Japanese physicist named Hideki Yukawa proposed something brilliant. Yukawa reasoned by analogy with electromagnetism. In the electromagnetic force, two charged particles interact by exchanging photons. Photons are the carrier particles of the electromagnetic field. When an electron repels another electron, it does so by exchanging virtual photons between them. The photon is massless, which is why the electromagnetic force has infinite range. A massless carrier particle can travel any distance. Yukawa asked a simple question. What if the nuclear force works the same way, with nucleons exchanging carrier particles? But what if those carrier particles have mass? This was the key insight. If the carrier particle has mass, it takes energy to create it, and the uncertainty principle allows that energy to be borrowed from the vacuum, but only for a very short time. The heavier the carrier particle, the shorter the time it can exist, and the shorter the distance it can travel before it must be reabsorbed. A massive carrier particle would create a force that is strong at short range, but drops off rapidly with distance. Exactly the behavior the nuclear force exhibits. Yukawa worked out the mathematics and predicted that the carrier particle of the nuclear force should have a mass roughly 200 times the mass of an electron, or about 1/7 the mass of a proton. He predicted this particle would come in 3 varieties: positively charged, negatively charged, and neutral. These particles were later discovered in cosmic ray experiments and in particle accelerators. They are called pions, short for p-mesons. A meson is a type of subatomic particle, and pions are the lightest mesons. The charged pions have a mass of about 140 megaelectronvolts, and the neutral pion has a mass of about 135 megaelectronvolts. Yukawa's prediction was remarkably accurate. He won the Nobel Prize in Physics in 1949 for this work. So here is how it works. Protons and neutrons inside the nucleus are constantly exchanging pions with each other. A proton can emit a positively charged pion and momentarily become a neutron. A neighboring neutron absorbs that pion and becomes a proton. Then the process reverses. The neutron emits a pion back, becomes a proton again, and the original particle absorbs it and becomes a neutron.
This exchange happens back and forth constantly at a frantic pace. Each exchange transfers momentum between the nucleons, and the net effect of this rapid exchange is an attractive force pulling the nucleons toward each other. This is not a metaphor. Pion exchange is a physical process. The pions are real particles, created and absorbed through the rules of quantum field theory. They are called virtual particles in this context because they exist only briefly during the exchange, popping into existence and being absorbed so quickly that they cannot be directly observed as free particles during the process. But their effects are absolutely real. The attractive force between nucleons is the measurable consequence of this constant pion exchange. Think of it this way. Imagine 2 ice skaters standing close together on a frozen lake. One skater throws a heavy ball to the other. When the first skater throws the ball, the recoil pushes them backward, away from the second skater. When the second skater catches it, the impact pushes them backward too, away from the first. In this scenario, exchanging the ball pushes them apart. That is roughly how photon exchange works in electromagnetic repulsion between like charges. But in quantum field theory, something counterintuitive happens. The mathematics allows the exchange to work in reverse under certain conditions, pulling the particles together instead of pushing them apart. Pion exchange between nucleons works this way. The net result of the exchange is attraction, not repulsion. The nucleons are drawn together, and the reason this attraction is short-ranged is directly because pions have mass. The heavier the exchanged particle, the shorter the distance over which the force operates. This relationship is quantitative. The range of the force is inversely proportional to the mass of the carrier particle. For pions, with their mass of about 140 megaelectronvolts, the range works out to roughly 1.4 femtometers. This matches beautifully with the observed range of the nuclear force. Beyond about 2 to 3 femtometers, the pion exchange mechanism effectively shuts off. This is profoundly different from how electromagnetism works. Photons are massless. They can travel forever, so the electromagnetic force reaches to infinity. Pions have mass. They can only survive for a tiny fraction of a second before they must be reabsorbed. They cannot travel far. So the nuclear force they carry is confined to the immediate neighborhood of the nucleon that emitted them. Now let us look at the actual tug-of-war inside the nucleus. Because what happens inside a nucleus is a competition between 2 forces that could not be more different in character. On one side, you have the electromagnetic force. It repels every proton from every other proton. It has infinite range, so every proton-proton pair in the nucleus contributes to the total repulsion. And the total electromagnetic energy grows rapidly as you add protons, because each new proton repels every proton that is already there. For a nucleus with Z protons, the total electromagnetic repulsion energy is roughly proportional to Z times Z minus 1. That grows fast. A nucleus with 10 protons has about 45 proton-proton pairs, all repelling each other. A nucleus with 50 protons has about 1,225 pairs. A nucleus with 92 protons, like uranium, has over 4,000 pairs. On the other side, you have the residual strong interaction. It attracts every nucleon to its nearest neighbors, but it does not reach across the entire nucleus. Each nucleon interacts strongly with only a handful of neighbors, maybe 4 or 5 or 6 in its immediate vicinity. Beyond that, the force falls off so sharply that distant nucleons might as well be on the other side of the universe. This means the total nuclear binding energy grows roughly proportionally with the total number of nucleons. If you double the number of nucleons, you roughly double the total strong force binding. It does not grow as fast as the repulsion does. The electromagnetic repulsion between protons grows roughly as the square of the proton count, while the nuclear attraction grows roughly linearly with the total nucleon count. This is why small nuclei are incredibly stable. In a helium nucleus, 2 protons and 2 neutrons, each nucleon is right next to every other nucleon. They are all within the range of the strong force. Every pair attracts. The electromagnetic repulsion between the 2 protons is real, but it is massively overpowered by the strong attraction between all 4 nucleons. The strong force wins by a huge margin. Helium nuclei are among the most tightly bound objects in nature. They are so stable that they get ejected as a unit when unstable heavy nuclei decay. That is what an alpha particle is. A helium nucleus, so tightly bound it acts like a single object. For medium-sized nuclei, like iron with 26 protons and 30 neutrons, the balance is still favourable. The strong force binds every nucleon to its neighbours, and while the electromagnetic repulsion between 26 protons is substantial, the nuclear attraction from all 56 nucleons is more than enough to compensate. Iron nuclei sit near the sweet spot of nuclear stability, where the binding energy per nucleon is at its maximum. We will explore that in more detail later. For now, the point is that medium-sized nuclei are stable because the strong force still dominates. But for very large nuclei, the balance starts to shift. Consider uranium with 92 protons and 146 neutrons. Each nucleon still attracts its nearest neighbours. The strong force is doing its job locally, but those 92 protons are repelling each other across the entire nucleus. A proton at one edge feels the electromagnetic push from protons at the opposite edge. Protons that are several femtometers away, too far for the strong force to reach, but well within range of the electromagnetic force. The long-range repulsion adds up across all 4,000 plus proton-proton pairs, and it starts to rival the total strong force binding. The nucleus is still bound, but just barely. It is teetering on the edge. And this is why uranium and other heavy elements are radioactive. Their nuclei are not fully stable. The electromagnetic repulsion is almost strong enough to overcome the nuclear binding. Given enough time, or the right trigger, the nucleus will break apart. There is a critical distance that governs this entire competition. At separations less than about 1 femtometer, nucleons actually repel each other through the strong force. There is a hard repulsive core that prevents nucleons from overlapping. This is important. Nucleons are not points. They have a finite size, roughly 1 femtometer across, and they resist being squeezed into the same space. Between about 1 and 2 femtometers, the strong force is powerfully attractive. This is the sweet spot, the distance at which nucleons prefer to sit relative to each other. Beyond 2.5 to 3 femtometers, the strong force drops essentially to zero, and only electromagnetic repulsion remains. So inside a stable nucleus, nucleons arrange themselves at separations of about 1 to 2 femtometers from their neighbors. Close enough for the strong force to bind them, far enough apart that the repulsive core does not push them away. Each nucleon sits in a potential well, created by the combined attraction of its neighbors, vibrating slightly around its equilibrium position like a ball sitting in a bowl. This gives the nucleus a property that might surprise you. Nuclear matter has a roughly constant density. No matter how many nucleons you add, the density stays about the same. A helium nucleus and a uranium nucleus have approximately the same density.
Adding more nucleons makes the nucleus bigger, not denser. This is because each nucleon only interacts with its nearest neighbors. Adding more nucleons just extends the structure outward. It does not compress what is already there. This is very different from a gravitationally bound object like a planet or star. In a planet, gravity pulls everything toward the center. The core is much denser than the surface. More mass means more compression. But in a nucleus, the strong force is short-ranged. There is no long-range pull toward the center. Each nucleon just sticks to its neighbors. The result is more like a liquid than a gravitational body or a crystalline solid. This analogy is not casual. Nuclear physicists take it seriously, and it turns out to be one of the most powerful conceptual tools in the field. Think about a drop of water. If you have a small drop and a large drop, the large drop has more water molecules. It is bigger, but the molecules inside it are packed at the same density as in the small drop. Water does not get denser when you collect more of it into a larger container. The molecules sit at a preferred spacing, determined by the balance between intermolecular attraction and short-range repulsion, and that spacing does not change no matter how much water you have. Add more water and the drop gets bigger. It does not get denser. The interior of a large puddle has the same density as the interior of a raindrop. Nuclear matter works the same way, and for the same fundamental reason. The strong force between nucleons has a preferred spacing, roughly 1 to 2 femtometers, set by the balance between attraction and the hard repulsive core. This spacing does not change when you add more nucleons. A helium nucleus with 4 nucleons and a uranium nucleus with 238 nucleons have the same internal density. The same staggering density we encountered earlier, packed into a space no larger than a few femtometers. The uranium nucleus is bigger, but it is not denser. The nucleons inside it are spaced the same way as in helium. This is called saturation, and it is a direct consequence of the short-range nature of the strong force. Because each nucleon only attracts its immediate neighbors, adding more nucleons to the system extends the structure outward without compressing the interior. There is no long-range pull drawing everything toward a common center. Each nucleon cares only about the handful of partners within a femtometer or two. Beyond that, it is oblivious. This is strikingly different from what you might intuitively expect. You might assume that cramming more particles into a nucleus would squeeze the ones already there into an even tighter space. That is what happens with gravity. Add mass to a star, and gravity compresses the core to higher densities. But the nucleus does not work that way. It grows outward like a liquid drop, maintaining constant density throughout. The nuclear liquid drop model, pioneered in the 1930s by George Gamow and refined by Carl von Weizsäcker, Niels Bohr, and others, uses this analogy as the foundation for understanding nuclear behavior. It treats the nucleus as a droplet of incompressible quantum fluid, with a well-defined surface and a constant interior density. This model successfully predicts nuclear sizes, binding energies, and even the process of nuclear fission, where a large nucleus splits in two like an overstretched droplet of water breaking apart under its own surface tension. The roughly constant density of nuclear matter means the radius of a nucleus is proportional to the cube root of the number of nucleons. Double the number of nucleons and the radius increases by about 26%. This has been confirmed by decades of scattering experiments where physicists fire electrons or other particles at nuclei and measure how they bounce off, mapping the size and shape of the nucleus with extraordinary precision. Let me return to pion exchange for a moment, because there is something about it that reveals how dynamic the nucleus really is. When a proton emits a pion and becomes a neutron, and a neighboring neutron absorbs the pion and becomes a proton, the identities of those two nucleons have swapped. The proton became a neutron, and the neutron became a proton. Inside a nucleus, this is happening constantly. Protons and neutrons are not sitting there with fixed identities. They are flickering back and forth, exchanging charge through pion exchange, swapping roles millions of times per second. The strong force does not distinguish between protons and neutrons in terms of its attractive strength. A proton attracts a neutron just as strongly as two neutrons attract each other, or two protons attract each other, as far as the strong force is concerned. This property is called charge symmetry, or more precisely, isospin symmetry, and it is a deep feature of the strong interaction. This means that from the perspective of the nuclear force, a proton and a neutron are essentially the same particle in two different charge states. They are two versions of a single entity, the nucleon. The strong force treats them identically. The only difference is that protons carry electric charge and participate in electromagnetic interactions, while neutrons do not. This distinction matters enormously for nuclear stability, as we will see, but for the strong force itself, protons and neutrons are interchangeable. This also explains something important about pion exchange. There are three kinds of pions: a positively charged pion, a negatively charged pion, and a neutral pion. When a proton emits a positively charged pion, it becomes a neutron. When a neutron absorbs that positively charged pion, it becomes a proton. But a proton can also exchange a neutral pion with another proton, remaining a proton throughout. And a neutron can exchange a neutral pion with another neutron. All three types of exchange contribute to the nuclear force. The details of how they combine determine the precise character of the attraction between different nucleon pairs. The Yukawa picture of pion exchange is a simplification. It captures the essential physics at distances of 1 to 2 femtometers, the range where pion exchange dominates. But at shorter distances, below about 1 femtometer, the picture becomes more complicated. Heavier mesons can be exchanged, not just pions. Particles like the rho meson, the omega meson, and the sigma meson all play roles at shorter ranges. These heavier particles have shorter ranges because of their greater mass, but they contribute additional attraction or repulsion depending on the specific meson and the distance. The full nuclear force, taking all these exchanges into account, is a complex function of distance with attractive and repulsive regions at different ranges. Nuclear physicists have spent decades mapping out this force in detail. They scatter protons and neutrons off each other at various energies and angles, measuring how the particles deflect. From these measurements, they reconstruct the force between nucleons as a function of distance. The result is called the nucleon-nucleon potential, and it has been measured with impressive precision. At very short distances, below about half a femtometer, the force is strongly repulsive. This is the hard core, the resistance of nucleons to being squeezed together. At about 1 femtometer, the force crosses zero and becomes strongly attractive. The attraction peaks at around 1 to 1.5 femtometers. Beyond 2 femtometers, it starts falling off rapidly. By 3 femtometers, it is negligible. This shape, the repulsive core transitioning to a strong attraction that then drops off exponentially, is what gives nuclear matter its characteristic properties. The repulsive core prevents collapse. The attraction at intermediate range provides binding.
The rapid fall-off beyond 2 to 3 femtometers ensures that nuclei have definite sizes and that the force does not extend beyond the nucleus. So here is the picture. Inside every nucleus heavier than hydrogen, a violent and ongoing competition is playing out. The electromagnetic force, reaching across the entire nucleus, pushes every proton away from every other proton with relentless repulsion. The residual strong interaction, operating only between nearest neighbours, pulls nucleons together with tremendous force. At short range, the strong interaction wins overwhelmingly. At long range, only electromagnetism survives. The nucleus exists because the strong force wins where it matters most, in the close packed interior where nucleons are touching their neighbours. It exists because the strong force can overpower the electromagnetic repulsion at the distances where nucleons actually sit. But the victory is not infinite. The strong force has limits. Its short range means it cannot scale up indefinitely. As nuclei grow larger, the electromagnetic repulsion, which does scale up, eventually begins to challenge the nuclear binding. This sets a limit on how large nuclei can be and determines which nuclei are stable and which are doomed to break apart. The nucleus is not a static object. It is a seething, dynamic system of protons and neutrons exchanging pions, flickering between identities, vibrating in their potential wells, held together by a force of staggering power and exquisite short range. It is the most tightly bound ordinary structure in nature, and it exists because of a competition between two forces that could not be more different, one with infinite reach and one that barely extends beyond the particles it binds. The balance between them governs the stability of every atom in the universe. But there is a piece of this puzzle we have not yet fully addressed. We have talked about protons and how they repel each other, and how the strong force overpowers that repulsion at close range. But what about neutrons? Neutrons carry no electric charge. They do not contribute to the electromagnetic repulsion at all. And yet, they are absolutely essential for nuclear stability. Without neutrons, no nucleus heavier than hydrogen could exist. Understanding why neutrons matter and how the ratio of neutrons to protons determines whether a nucleus lives or dies is what we need to explore next. Neutrons are easy to overlook. They carry no electric charge. They do not repel each other. They do not repel protons. In the early days of nuclear physics, after James Chadwick discovered the neutron in 1932, it was tempting to think of neutrons as filler, passive stuffing, extra mass sitting inside the nucleus without doing much of anything important, just dead weight that happened to be there because nature put it there. That picture could not be more wrong. Neutrons are not passive. They are not filler. They are absolutely essential for the existence of nearly every element in the periodic table. Without neutrons, the only nucleus that could exist would be a single proton, the nucleus of hydrogen. Every other element, from helium to carbon to iron to gold to uranium, requires neutrons. And not just a few neutrons here and there. As elements get heavier, the proportion of neutrons in the nucleus must increase. Light nuclei like carbon have roughly equal numbers of protons and neutrons. But by the time you reach LED 208, one of the most stable heavy nuclei in nature, there are 126 neutrons compared to 82 protons. That is more than 1.5 neutrons for every proton. Heavy nuclei need a neutron surplus to survive. Understanding why reveals something beautiful about the physics governing nuclear stability. Let us start with the simplest reason neutrons matter. They contribute to the strong force binding without adding any electromagnetic repulsion.
A neutron inside a nucleus attracts its neighbouring nucleons through the residual strong interaction with exactly the same strength as a proton does.
The nuclear force does not care about electric charge. A neutron attracts a proton just as powerfully as a proton attracts a proton, or a neutron attracts a neutron. All nucleon-nucleon pairs feel the same strong attraction. But a neutron, unlike a proton, adds zero electromagnetic repulsion. It is electrically neutral. It does not push against any of the protons in the nucleus. So every neutron you add to a nucleus increases the total binding energy from the strong force without increasing the electromagnetic energy trying to tear the nucleus apart. Neutrons are pure binding, all gain, no cost, at least from the electromagnetic perspective. This is why you cannot build a stable nucleus from protons alone. Consider what would happen if you tried to make a helium nucleus using 4 protons instead of 2 protons and 2 neutrons. All 4 protons would attract each other through the strong force, but all 4 would also repel each other electromagnetically. The electromagnetic repulsion energy of 4 protons is 6 times the repulsion between a single proton pair, because there are 6 unique proton-proton pairs in a group of 4. That is a tremendous amount of repulsion for such a tiny system. In reality, a 4-proton nucleus does not exist. It would fly apart instantly. Nature solved this problem by replacing 2 of those protons with neutrons. 2 protons and 2 neutrons give you helium-4, the alpha particle. The neutrons contribute just as much strong force binding as the protons they replaced, but they eliminated 5 of the 6 repulsive proton-proton pairs. Only 1 pair of protons remains. The binding is preserved, the repulsion is slashed, the nucleus is stable. This principle scales up across the entire periodic table. As you build heavier nuclei, you need to add protons to create new elements. Each new proton brings its positive charge into the nucleus, repelling every other proton already there. To compensate, you need to add neutrons. Extra neutrons provide additional strong force attraction without adding more electromagnetic repulsion. They dilute the effect of the protons. They spread out the nuclear binding over more nucleon pairs while keeping the electromagnetic cost from growing too fast. But here is something that makes neutrons even more fascinating. A free neutron, one that is not inside a nucleus, is unstable. Left on its own, a neutron will decay in roughly 10 minutes. It transforms into a proton, emitting an electron and an antineutrino in the process. 10 minutes. That is all a neutron gets before it falls apart. If you could somehow collect a handful of free neutrons and set them on a table, half of them would be gone in about 10 minutes. The rest would follow shortly after. And yet, inside a nucleus, neutrons can last forever. A neutron sitting inside a stable nucleus like LED 208 has been there for billions of years and will remain there for billions more. It shows no sign of decaying. It is perfectly stable. How is that possible? How can a particle that falls apart in 10 minutes on its own survive for the age of the universe when surrounded by other nucleons? The answer is energy. When a free neutron decays into a proton, it releases energy. The proton plus the electron plus the antineutrino weighs slightly less than the neutron, and the difference is released as kinetic energy. The decay is energetically favorable. Nature allows it because the products have lower total energy than the original neutron. But inside a stable nucleus, the situation reverses. The neutron is sitting in a low energy state, bound tightly to its neighbors. For that neutron to decay into a proton, the new proton would need to find an available energy level in the proton energy structure of that nucleus. If all the low energy proton levels are already filled, the new proton would have to occupy a high energy level. That costs energy. If the energy cost of placing the new proton into a high level exceeds the energy gained from the neutron decaying, the decay cannot happen. Nature does not allow it, because the products would have higher total energy than the original configuration. The decay is blocked. The neutron is trapped in stability by the very nucleus that surrounds it. This is a beautiful example of how the nuclear environment transforms the properties of individual particles. A neutron in isolation is fragile. A neutron inside a well-balanced nucleus is effectively immortal. The nucleus does not just hold neutrons in place physically, it changes their fundamental behavior. It stabilizes them by making their decay energetically impossible. But there is a limit to how many neutrons you can add, and understanding that limit requires a principle from quantum mechanics. It is called the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. The Pauli exclusion principle states that no two identical particles can occupy the same quantum state simultaneously. Protons and neutrons are both fermions, particles that obey this rule. This means that inside the nucleus, protons fill energy levels and neutrons fill energy levels, and no two protons can share the same level and no two neutrons can share the same level. Think of it like a building with floors. Protons have their own building and neutrons have their own building. Each floor can hold only a limited number of occupants, usually two, one with spin up and one with spin down. As you add protons, they fill the lowest available floors first, then the next floors, and so on, stacking up through higher and higher energy levels. Neutrons do the same in their own separate building. Now here is the key. If you have far more neutrons than protons, the neutron building fills up to much higher floors than the proton building. Those neutrons occupying high energy levels have a lot of energy. Conversely, the proton building has many empty low energy floors. Nature prefers the lowest energy configuration. If a neutron sitting on a high floor in the neutron building could somehow become a proton and drop into a low empty floor in the proton building, the total energy of the system would decrease. The nucleus would be more tightly bound. And nature has exactly this mechanism. It is called beta decay. In beta-minus decay, a neutron inside the nucleus transforms into a proton. It emits an electron and an antineutrino in the process. The neutron disappears and a proton takes its place, filling a lower energy level in the proton building. The total energy decreases and the nucleus moves toward a more stable configuration. The reverse process also exists. In beta plus decay, a proton transforms into a neutron, emitting a positron and a neutrino. This happens when there are too many protons relative to neutrons. The proton building is filled to higher levels than the neutron building, and a proton can lower the system energy by converting into a neutron and dropping into a lower neutron energy level. This is why the neutron-to-proton ratio matters so much. If there are too many neutrons, the nucleus undergoes beta-minus decay, converting neutrons to protons until the energy levels balance. If there are too many protons, the nucleus undergoes beta-plus decay, or electron capture, converting protons to neutrons. Stable nuclei sit at the balance point, where the energy levels of protons and neutrons are roughly equalized. Any deviation from that balance and the nucleus will decay, adjusting its composition until it finds stability. For light elements, this balance point is approximately 1:1. Carbon-12 has 6 protons and 6 neutrons. Nitrogen-14 has 7 protons and 7 neutrons. Oxygen-16 has 8 protons and 8 neutrons. Equal numbers. But as you go to heavier elements, the balance shifts. You need progressively more neutrons than protons. Iron-56 has 26 protons and 30 neutrons, a ratio of about 1.15 neutrons per proton. Tin, one of the heavier stable elements, has 50 protons and can have anywhere from 62 to 74 neutrons in its various stable forms. Lead-208 has 82 protons and 126 neutrons, a ratio of about 1.54. The reason the ratio must increase for heavy elements is the electromagnetic repulsion. More protons means more repulsion. The only way to compensate is to add extra neutrons, which provide additional binding without additional repulsion. But each extra neutron beyond the balanced ratio fills a higher energy level, and at some point, the energy cost of adding more high-energy neutrons exceeds the benefit of the extra binding they provide. There is an optimal ratio for each element, and that optimal ratio increases steadily with atomic number. This brings us to one of the most important concepts in nuclear physics: binding energy per nucleon. This single quantity tells you how tightly a nucleus is bound, and crucially, which nuclei are the most stable in all of nature. The total binding energy of a nucleus is the energy you would need to supply to completely disassemble it, to pull every proton and neutron apart and separate them to infinite distance. A higher binding energy means a more tightly bound nucleus. But total binding energy is not the best measure of stability, because bigger nuclei naturally have more binding energy, simply because they have more nucleons. A more useful quantity is the binding energy per nucleon. You take the total binding energy and divide by the number of nucleons. This tells you, on average, how tightly each individual nucleon is held in the nucleus. When you plot binding energy per nucleon against the number of nucleons for every known nucleus, you get one of the most famous curves in all of physics. It rises steeply for light nuclei, peaks around iron and nickel, and then gradually declines for heavier nuclei. This curve is a map of nuclear stability. Nuclei near the peak are the most stable objects in nature. Nuclei on either side of the peak are less stable and can release energy by moving toward the peak. Let us walk along this curve slowly, because the shape tells a story. Hydrogen 1, a single proton, has zero binding energy because there is nothing to bind. It is just one particle sitting alone. Add a neutron and you get deuterium, hydrogen with one proton and one neutron. The binding energy per nucleon is about 1.1 mega-electron volts, not very tightly bound. The two nucleons are holding on to each other, but just barely. Deuterium is the weakest bound stable nucleus in nature. It takes only 2.2 mega-electron volts to break it apart, which is modest by nuclear standards. Jump to helium-4, 2 protons and 2 neutrons, and the binding energy per nucleon shoots up to about 7.1 mega-electron volts. That is a massive jump from deuterium. Helium-4 is remarkably stable for its size. In fact, it is so much more stable than its immediate neighbours on the curve that it stands out like a spike. Lithium and beryllium, the next elements up, actually have lower binding energies per nucleon than helium. The curve dips after helium before resuming its climb. This spike at helium-4 is a clue that something special is happening, and that something is the magic numbers, which we will return to shortly. The extraordinary stability of helium-4 is why alpha particles are so common in nuclear decay. When a heavy nucleus needs to shed mass, it does not eject random nucleons one at a time. It ejects helium-4 nuclei, because those 4 nucleons are so tightly bound together that it costs less energy to package them up and launch them out as a unit than to rip them apart individually. Continue up the periodic table. Carbon-12 has about 7.7 mega-electron volts per nucleon. Oxygen-16 has about 8.0. The curve keeps climbing, each nucleus a little more tightly bound per nucleon than the last. But notice that the curve is flattening out. The steep rise from hydrogen to helium has mellowed into a gentle slope. Each additional nucleon adds a little more binding, but the gains are getting smaller. The peak comes around iron-56 and nickel-62. Iron-56 has a binding energy per nucleon of about 8.79 mega-electron volts. Nickel-62 is actually the most tightly bound nucleus per nucleon in nature, at about 8.795 mega-electron volts, edging out iron-56 by a tiny margin. Iron-58 is close behind. This region around iron and nickel represents the most stable nuclear matter possible. These nuclei sit at the bottom of the valley of nuclear stability. They are the end point of nuclear energy release. You cannot extract energy from iron or nickel by either combining them or splitting them. They are the ashes of nuclear burning. This is a profound fact. It means there is a destination, an end point, a ground floor that nuclear matter is always trying to reach. Light nuclei want to fuse and become heavier, moving toward iron. Heavy nuclei want to split and become lighter, also moving toward iron. Iron is the final state, the most relaxed, most comfortable, lowest energy configuration that nuclear matter can achieve. Everything in the universe, every nuclear process in every star, in every reactor, in every radioactive decay chain, is either climbing toward iron from below or rolling downhill toward iron from above. Beyond iron, the curve begins to decline. As nuclei get heavier, the binding energy per nucleon slowly drops. Lead-208 has about 7.9 megaelectron volts per nucleon. Uranium-238 has about 7.6. The trend is clear. Heavier nuclei are less tightly bound per nucleon than iron. They are sitting on the downslope of the stability curve. They have more energy per nucleon than they would if they were closer to iron. That excess energy is available for release, which is why heavy nuclei can undergo fission and why radioactive decay is so common among the heaviest elements. This curve explains the two great nuclear energy processes in nature: fusion and fission. They work by moving nuclei toward the peak of the curve. Fusion takes light nuclei, which sit on the left side of the curve, and combines them into heavier nuclei closer to the peak. When you fuse two hydrogen nuclei into helium, you are climbing the steep left side of the curve. The product is more tightly bound per nucleon than the starting materials. The difference in binding energy is released as kinetic energy and radiation. This is the energy source of every star in the universe. Stars spend most of their lives fusing hydrogen into helium, climbing the binding energy curve, releasing the energy that makes them shine. Massive stars can continue fusing heavier elements, carbon, oxygen, silicon, climbing steadily toward the peak. But the process stops at iron. You cannot release energy by fusing iron into anything heavier because you would be going down the curve, not up. Iron is the end of the road for stellar fusion. When a massive star builds an iron core, it can no longer generate energy through fusion. The core collapses, and the star explodes as a supernova. Fission works from the other direction. It takes very heavy nuclei, which sit on the right side of the curve, and splits them into lighter nuclei closer to the peak. When you split a uranium nucleus into two medium-sized fragments, those fragments are more tightly bound per nucleon than the original uranium. The difference in binding energy is released. This is the energy source of nuclear reactors and nuclear weapons. Fission releases energy because the products sit closer to the peak of the curve than the starting material does. Both processes, fusion and fission, are driven by the same principle. Nuclei release energy when they move toward iron on the binding energy curve. Light nuclei release energy by getting heavier. Heavy nuclei release energy by getting lighter. Iron and nickel sit at the bottom of the energy valley, the most stable configuration, the place where no more nuclear energy can be squeezed out. Now, let us talk about why heavy nuclei fall apart. We have already touched on this, but the full picture involves several different mechanisms. The fundamental reason is always the same. The nucleus is seeking a more stable configuration, one with more binding energy per nucleon, one closer to the valley of stability. Alpha decay is the most dramatic. In alpha decay, a heavy nucleus ejects an alpha particle, a helium-4 nucleus, 2 protons and 2 neutrons bound together. The alpha particle is ejected because it is an extraordinarily tightly bound unit. It costs relatively little energy to assemble 2 protons and 2 neutrons into an alpha particle inside the nucleus, and once assembled, the alpha particle can tunnel through the potential barrier created by the nuclear force and escape. When the alpha particle leaves, it carries away 2 protons and 2 neutrons. The remaining nucleus is lighter by 4 nucleons and has 2 fewer protons. This reduces the electromagnetic repulsion in the remaining nucleus, making it more stable. The total binding energy per nucleon of the products, the daughter nucleus plus the alpha particle, is higher than the binding energy per nucleon of the original parent nucleus. Energy is released. The system has moved closer to stability. Alpha decay is common in the heaviest elements. Uranium, thorium, radium, polonium all undergo alpha decay. Some decay chains involve a long series of alpha decays, each one reducing the nucleus by 4 nucleons and 2 protons, stepping down through the periodic table until finally reaching a stable nucleus. Uranium-238, for example, decays through a chain of 14 steps, involving 8 alpha decays and 6 beta decays, before finally arriving at lead-206, a stable nucleus. Beta decay, which we discussed earlier, is the other major decay mode. It does not change the total number of nucleons in the nucleus. Instead, it converts a neutron into a proton or a proton into a neutron, adjusting the neutron-to-proton ratio toward the optimal balance for that particular number of nucleons. Beta decay moves the nucleus sideways on the chart of nuclides, keeping the mass number fixed but changing the element. It is the mechanism by which nuclei correct their internal composition. Henri Becquerel discovered radioactivity in 1896, observing that uranium salts emitted penetrating radiation spontaneously without any external stimulus. Marie Curie and her husband Pierre pursued this discovery, identifying new radioactive elements including polonium and radium. At the time, nobody understood why certain elements were radioactive. It seemed random. Some elements decayed and others did not, with no obvious pattern. But now we understand that radioactivity is not random at all. It is a direct consequence of the binding energy curve and the competition between the strong force and electromagnetic repulsion. Nuclei decay when they are not at the most stable configuration for their number of nucleons. They are seeking lower energy. They are trying to roll downhill toward the valley of stability. There is a boundary on the periodic table beyond which no nucleus is permanently stable. Bismuth-209 was long considered the heaviest stable nucleus, with 83 protons and 126 neutrons. In 2003, physicists discovered that bismuth-209 is actually radioactive, but with a half-life of roughly 19 billion years, more than 1 billion times the age of the universe. For all practical purposes, it is stable, but technically, no element heavier than lead has a truly stable isotope. Lead-208, with 82 protons and 126 neutrons, is the heaviest nucleus that is genuinely stable on any timescale. Why does stability end there? Because of the relentless scaling of electromagnetic repulsion. Remember, the strong force binds locally. Each nucleon attracts only its nearest neighbours. The total strong force binding grows roughly in proportion to the total number of nucleons, but the electromagnetic repulsion grows roughly as the square of the number of protons. Every new proton repels every proton already present. For small nuclei, the strong force dominates easily. For medium nuclei, it still wins, but by a smaller margin. For heavy nuclei, the margin gets thinner and thinner. Beyond lead, the electromagnetic repulsion has grown so large relative to the strong force binding that no arrangement of protons and neutrons can produce a permanently stable configuration. The nucleus can always find a way to release energy by shedding particles or rearranging its internal structure. It may take an astronomically long time, as with bismuth, but it will eventually happen. The chart of nuclides, which plots every known nucleus according to its number of protons and neutrons, reveals a striking pattern. Stable nuclei form a narrow band called the valley of stability. For light elements, this band follows the line where the number of neutrons equals the number of protons. For heavier elements, the band curves upward, requiring progressively more neutrons than protons. On either side of this narrow band, nuclei are unstable. Too many neutrons relative to protons, and the nucleus undergoes beta- decay, converting neutrons to protons. Too few neutrons, and the nucleus undergoes beta+ decay, or electron capture, converting protons to neutrons. Too heavy overall, and the nucleus undergoes alpha decay, shedding mass to move closer to the stable region. The valley of stability is not arbitrary. It is carved by the precise competition between the strong force, the electromagnetic force, and the Pauli exclusion principle. Change any of these, even slightly, and the valley would shift. The elements that exist, the atoms that make up planets and stars and living things, are determined by the exact balance of these forces. If the strong force were 5% weaker, many nuclei we consider stable would become unstable. The periodic table would be shorter. The chemistry of life might be impossible. If the strong force were 5% stronger, more heavy elements would be stable. The periodic table would extend further. Entirely different chemistry might emerge. There are also special numbers of protons or neutrons that confer extra stability. These are called magic numbers. 2, 8, 20, 28, 50, 82, and 126. Nuclei with a magic number of protons or a magic number of neutrons, or especially both, are exceptionally stable. They have higher binding energy per nucleon than their neighbours on the chart. They are less likely to undergo radioactive decay. They are more abundant in nature. The evidence for magic numbers is striking. Look at the elements that have the most stable isotopes. Tin, with 50 protons, a magic number, has 10 stable isotopes, more than any other element. Lead, with 82 protons, another magic number, has 4 stable isotopes and is the heaviest element with any stable isotopes at all. Calcium, with 20 protons, has 5 stable isotopes and is unusually abundant for its size. The pattern is unmistakable. When you hit a magic number, stability jumps. Neutron magic numbers show the same effect. Nuclei with 50 neutrons, 82 neutrons, or 126 neutrons are disproportionately stable compared to their neighbours with one more or one fewer neutron. The most dramatic effect comes when both the proton number and the neutron number are magic. These doubly magic nuclei are islands of extraordinary stability in a sea of less stable configurations. Lead-208 is doubly magic. It has 82 protons and 126 neutrons. Both are magic numbers. This is why Lead-208 is the heaviest stable nucleus. Its double magic status gives it extra stability that carries it beyond where ordinary nuclei would have become radioactive. Helium-4 is also doubly magic, with 2 protons and 2 neutrons. This explains why the alpha particle is so tightly bound and why it is ejected as a unit in alpha decay. Oxygen-16, with 8 protons and 8 neutrons, is another doubly magic nucleus, and it is one of the most abundant elements in the universe. Calcium-40, with 20 protons and 20 neutrons, is yet another. The universe is built preferentially from doubly magic nuclei because they are the most stable building blocks nature can produce. Magic numbers arise from the shell structure of the nucleus. Just as electrons in an atom fill energy shells, With certain numbers of electrons producing the exceptionally stable noble gases, nucleons in a nucleus fill energy shells. When a shell is completely filled, the nucleus is especially stable. There is an energy gap between the filled shell and the next available level, and that gap makes it energetically costly to add another nucleon or to rearrange the existing ones. The magic numbers correspond to these filled nuclear shells. The physics is analogous to atomic shell structure, but the details are different because the forces involved are different. In atoms, the electromagnetic force from the central nucleus creates a well-defined potential that determines the shell structure. The math is relatively clean because there is one dominant source of force at the center. In nuclei, there is no central force source. Every nucleon interacts with every other nucleon through the strong force. The potential each nucleon feels is created by all the other nucleons collectively. Despite this complexity, clear shell structure emerges. Nucleons organize themselves into energy levels with gaps at the magic numbers, producing pockets of enhanced stability that are visible across the entire chart of nuclides. Let us come back to the big picture. The nucleus is a system of protons and neutrons bound together by the residual strong interaction. Protons contribute both strong force attraction and electromagnetic repulsion. Neutrons contribute strong force attraction without electromagnetic repulsion. The balance between these contributions, governed by quantum mechanics through the Pauli exclusion principle and shell structure, determines which nuclei are stable and which are not. Stable nuclei sit in the valley of stability on the chart of nuclides, with an optimal ratio of neutrons to protons for their size. Unstable nuclei lie outside this valley and undergo radioactive decay to move toward it. The binding energy per nucleon peaks near iron and nickel, making these the most stable nuclei in nature. Lighter nuclei can release energy through fusion. Heavier nuclei can release energy through fission. Both processes drive nuclei toward the peak of the binding energy curve.
The periodic table of elements, that chart hanging in every chemistry classroom, is ultimately a map of nuclear stability. Every element on it exists because its most common isotopes have nuclei that are either permanently stable or long-lived enough to persist over astronomical timescales. The identity of each element is defined by its number of protons. The stability of each isotope is determined by its number of neutrons, and the underlying physics governing all of it is the competition between the strong force that binds nucleons together and the electromagnetic force that tries to push protons apart. But we have been treating protons and neutrons as fundamental objects, as if they are the deepest level of the story. They are not. Protons and neutrons are themselves composite particles, built from smaller constituents held together by an even deeper force. The residual strong interaction that binds nucleons into nuclei is not itself the fundamental strong force. It is a shadow of something more powerful happening inside each proton and neutron. Understanding what lies beneath the nucleon, what protons and neutrons are actually made of, and how the nuclear force emerges from that deeper structure takes us to the final layer of this story, and it changes the picture entirely. We have been talking about protons and neutrons as if they are the end of the story. Solid little particles rattling around inside the nucleus, exchanging pions, attracting and repelling each other. And at the scale of nuclear physics, that picture works remarkably well. It explains binding energies, it explains radioactive decay, it explains why certain nuclei are stable and others are not. But it is not the deepest layer of reality. Protons and neutrons are not fundamental. They are not the bottom of the ladder. They are composite objects built from smaller, more elementary particles. And the force that binds the nucleus together is not itself fundamental either. It is a residual effect, a shadow, a faint echo of something far more powerful happening inside each nucleon. This deeper story begins in the early 1960s,
when physicists started noticing that there were far too many supposedly fundamental particles. The proton and neutron were just two members of a growing zoo of particles discovered in cosmic ray experiments and particle accelerators. There were pions, kaons, sigma particles, delta particles, omega particles, dozens and dozens of them. Each one seemed to be its own thing, with its own mass and properties. It was messy. It looked nothing like a fundamental theory should look. A truly fundamental theory should have a small number of building blocks, not an ever-expanding catalogue. In 1964, two physicists independently proposed a solution. Murray Gell-Mann and George Swig suggested that all these particles, protons, neutrons, pions, and the entire zoo, were not fundamental at all. They were built from a smaller set of truly elementary particles. Gell-Mann called them quarks. The idea was elegant. Instead of hundreds of fundamental particles, you needed only a handful of quarks combining in different ways to produce all the observed particles. The model proposed that protons and neutrons are each made of 3 quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Up quarks carry a positive electric charge of plus 2/3 of the proton charge. Down quarks carry a negative charge of minus 1/3. Add up the charges in a proton, 2/3 plus 2/3 minus 1/3, and you get plus 1, exactly the proton's charge. Add up the charges in a neutron, 2/3 minus 1/3 minus 1/3, and you get 0, exactly the neutron's charge. The arithmetic works perfectly. Pions, the particles that mediate the nuclear force between nucleons, are also made of quarks. But pions contain only 2 quarks, specifically 1 quark and 1 antiquark. A positively charged pion is an up quark paired with a down antiquark. A negatively charged pion is a down quark paired with an up antiquark. A neutral pion is a quantum mixture of up quark with up antiquark and down quark with down antiquark. Particles made of 3 quarks are called baryons. Particles made of a quark and an antiquark are called mesons. Protons and neutrons are baryons. Pions are mesons. The entire particle zoo sorts neatly into these 2 categories. But what holds the quarks together inside a proton or neutron? This is where a new and deeper force enters the picture. It is called the color force, or more formally, the strong interaction, described by the theory of quantum chromodynamics, or QCD. Do not be confused by the word color. Quarks are not literally colored. The term is a label for a type of charge that has nothing to do with visible light. Just as electric charge comes in 2 types, positive and negative, the charge associated with the color force comes in 3 types. Physicists call them red, green, and blue, borrowing the names of the primary colors of light. Every quark carries one of these 3 color charges. Antiquarks carry the corresponding anticolors: anti-red, anti-green, and anti-blue. The particles that carry the color force are called gluons. They are analogous to photons in electromagnetism. Photons carry the electromagnetic force between electrically charged particles. Gluons carry the color force between color-charged particles. But gluons are far stranger than photons. Photons are electrically neutral. They carry the force, but do not themselves feel it. Gluons, by contrast, carry color charge themselves. A gluon is not neutral. It carries 1 color and 1 anticolor simultaneously. This means gluons interact with each other, not just with quarks. Photons pass through each other without interacting. Gluons grab onto each other. This self-interaction
is what makes the color force so radically different from electromagnetism and so much more powerful. The color force has a bizarre property called confinement. You cannot isolate a single quark. You cannot pull a quark out of a proton and hold it up on its own. If you try to separate two quarks by pulling them apart, the color force between them does not weaken with distance the way electromagnetism does. Instead, it stays constant or even increases. The energy stored in the gluon field between them grows as you pull them apart. Eventually, so much energy builds up in the stretching gluon field that the energy converts into mass, creating a new quark-antiquark pair from the vacuum. Instead of freeing a quark, you have created new quarks. The original quarks snap back into bound states. New particles appear. But no free quark ever emerges. This is why quarks were so hard to discover. You cannot see them individually. You cannot isolate them. You can only infer their existence from the patterns they create inside the particles they build. It took years of experiments at particle accelerators, firing high-energy electrons at protons and studying how they scattered, to confirm that protons have internal structure. These deep inelastic scattering experiments, performed in the late 1960s and early 1970s at the Stanford Linear Accelerator Center, revealed that the proton is not a smooth, uniform blob. It contains three hard, point-like objects inside it. The electrons were bouncing off something small and dense within the proton, just as Rutherford's alpha particles had bounced off something small and dense within the atom decades earlier. History was repeating itself at a deeper scale. And this brings us to one of the most extraordinary facts in all of physics. A fact so strange that even many science enthusiasts do not know it. The quarks inside a proton are nearly massless. An up quark has a mass of only about 2 mega-electron-volts. A down quark has a mass of about 5 mega-electron-volts.
Add up the masses of 2 up quarks and 1 down quark, and you get roughly 9 mega-electron-volts. But a proton has a mass of 938 mega-electron-volts. The quarks account for less than 1% of the proton's mass. Less than 1%. So where does the other 99% come from? It comes from energy. Specifically, it comes from the energy of the gluon field that binds the quarks together, and from the kinetic energy of the quarks as they move inside the proton at enormous speeds. Einstein showed that energy and mass are equivalent. Energy has mass. And the energy contained in the churning, seething gluon field inside a proton is so enormous that it accounts for virtually all of the proton's mass. Let that sink in for a moment. When you step on a scale and see your weight, you are measuring the gravitational pull on the mass of your atoms. Almost all of that mass comes from the protons and neutrons in your nuclei. And almost all of the mass of those protons and neutrons comes not from solid stuff, not from particles with intrinsic heaviness, but from the energy of confinement, from the energy stored in the gluon fields that trap nearly massless quarks inside every nucleon in your body. You are not made of stuff, not in the way you intuitively think. You are made of energy, bound energy, trapped energy. Energy locked into a tiny space by the most powerful force in nature, manifesting as mass because Einstein's relationship between energy and mass says it must. The solidity you feel when you press your hand against a table is ultimately the resistance of energy fields, not the resistance of material substance. There is almost no material substance. There is almost entirely energy, organized by the color force into structures so stable they have lasted since the first seconds after the Big Bang. This is not a metaphor or a poetic exaggeration. It is a quantitative, measured fact. Lattice QCD calculations, performed on the most powerful supercomputers in the world,
have computed the mass of the proton from first principles by simulating the behavior of quarks and gluons on a discrete grid of spacetime points. These calculations confirm that the proton's mass arises overwhelmingly from the energy of the gluon field and the kinetic energy of the quarks. The intrinsic masses of the quarks themselves contribute almost nothing. The mass of everything around you, the mass of every planet, every star, every galaxy, is almost entirely the energy of confinement. Now here is the critical connection to the nucleus. The force that binds quarks together inside protons and neutrons is the fundamental color force carried by gluons. But the force that binds protons and neutrons together inside nuclei, the residual strong interaction we discussed earlier, is not the color force itself. It is a residual effect, a leftover, a secondary consequence of the color force leaking out of the nucleon. The analogy that makes this clearest involves electromagnetism. Consider two atoms. Each atom is electrically neutral overall. The positive charge of the nucleus exactly cancels the negative charge of the electrons. So, from far away, each atom has zero net charge and should feel no electromagnetic force from the other atom. But up close, the story changes. The charges inside each atom are not in exactly the same location. The positive nucleus is here, the negative electrons are there. This creates slight imbalances. The positive part of one atom can be slightly closer to the negative part of another atom, creating a weak attraction. This is called the van der Waals force. It is a residual electromagnetic effect between neutral objects. The fundamental force is electromagnetism inside the atoms. The residual force is the van der Waals attraction between the atoms. The nuclear force works the same way, one level deeper. Each proton and neutron is color neutral overall. The three quarks inside carry one red, one green, and one blue charge, which combine to make white, meaning no net color charge. From far away, a nucleon looks color neutral and should feel no color force from another nucleon. But at distances of 1 to 2 femtometers, when nucleons inside a nucleus are practically touching, the internal color charges are close enough that they do not perfectly cancel from the perspective of a neighboring nucleon. The quarks and gluons inside one nucleon interact with the quarks and gluons inside a neighboring nucleon. This creates an attraction. The pion exchange picture from Hideki Yukawa's theory is an effective description of this residual interaction. Pions themselves are quark-antiquark pairs, and their exchange between nucleons is ultimately a rearrangement of quarks and gluons between the two nucleon systems. So the hierarchy is this. The most fundamental force is the color force between quarks, carried by gluons, described by QCD. This force binds quarks into protons, neutrons, and other particles. The residual strong interaction is the leftover effect of the color force between color-neutral nucleons. It binds nucleons into nuclei. It is weaker than the fundamental color force, just as van der Waals forces are weaker than the electromagnetic forces inside atoms. But it is still enormously powerful by the standards of all other forces, powerful enough to overpower electromagnetism at nuclear distances and hold the nucleus together. This distinction matters because it tells us that nuclear physics and particle physics are different layers of the same reality. Nuclear physics describes what happens at the scale of femtometers, where protons and neutrons interact as whole objects exchanging pions and other mesons. Particle physics describes what happens at even smaller scales inside the nucleons, where quarks and gluons interact directly through the color force. Both descriptions are valid in their respective domains. The nuclear force is not wrong. It is an effective description that works beautifully at nuclear scales. But it emerges from a deeper structure, just as chemistry emerges from atomic physics, and atomic physics emerges from nuclear and particle physics. Now let us correct another misconception. The The nucleus is not a rigid object. It is not a fixed arrangement of billiard balls sitting motionless in a tiny space. Nuclei are dynamic, restless systems in constant motion. Nucleons inside the nucleus are moving. They vibrate, they oscillate, they rotate collectively. The nucleus has excited states, higher energy configurations it can temporarily occupy, just as atoms have excited electronic states. When a nucleus drops from an excited state to a lower energy state, it emits a gamma ray, a high-energy photon. This is gamma radiation, and it is a direct window into the energy level structure of the nucleus. Nuclei can deform. Not all nuclei are spherical. Many are slightly elongated or flattened, shaped more like a football or a discus than a perfect sphere. Some nuclei have permanent deformations, sitting in states that are not spherically symmetric. Others can be temporarily deformed by excitation, stretching and squashing before returning to their ground state shape. There are nuclei that vibrate like a shaking water droplet, oscillating between prolate and oblate shapes. There are nuclei that rotate collectively, the entire system of nucleons spinning as a unit, producing a characteristic pattern of energy levels that nuclear physicists can measure with exquisite precision. This richness of behavior is why nuclear physics remains an active and vibrant field of research. The nucleus is not a solved problem. There are thousands of known isotopes, and new ones are being created in laboratories around the world. Each isotope has its own set of energy levels, its own decay properties, its own shape and internal dynamics. Understanding all of this from first principles, starting from the interactions between individual nucleons, is an enormously complex computational challenge. Nuclear physicists use powerful supercomputers to simulate nuclear structure, and even then, exact solutions are possible only for the lightest nuclei. For heavier nuclei, approximations and models are essential. Let us talk about where nuclear physics meets the cosmos. Because the nucleus is not just an object studied in laboratories, it is the engine driving the most dramatic processes in the universe. Every star you see in the night sky is powered by nuclear fusion. Deep in the core of a star, temperatures reach tens of millions of degrees and pressures are enormous. Under these conditions, hydrogen nuclei, single protons, are moving fast enough to overcome their electromagnetic repulsion and get close enough for the residual strong interaction to grab them. They fuse. In the Sun, the dominant process is called the proton-proton chain. It is a series of reactions that ultimately converts 4 protons into one helium-4 nucleus, releasing energy in the form of gamma rays, positrons, and neutrinos. The energy comes from the difference in binding energy per nucleon between hydrogen and helium. Helium is more tightly bound per nucleon. The excess energy is released, and it is this energy, generated in the Sun's core, that works its way outward over hundreds of thousands of years and eventually reaches Earth as sunlight. Every second, the Sun converts roughly 600 million tons of hydrogen into helium. In doing so, it converts about 4 million tons of mass directly into energy, following Einstein's famous relationship between energy and mass. 4 million tons of matter annihilated every second, converted to pure energy. And the Sun has been doing this for 4.5 billion years. It has enough hydrogen fuel to continue for roughly another 5 billion years. The energy that warms your skin, that grows your food, that drives Earth's weather and climate, all of it comes from nuclear fusion, from the strong force binding nucleons together inside the Sun's core. Massive stars, those much heavier than the Sun, burn through their hydrogen faster and then move on to fusing heavier elements. After hydrogen comes helium fusion, producing carbon and oxygen, then carbon fusion, producing neon and magnesium, then oxygen fusion, producing silicon and sulfur, then silicon fusion, producing iron. Each stage releases energy because each product is closer to the peak of the binding energy curve. But each successive stage is less efficient and lasts for a shorter time. A massive star might burn hydrogen for millions of years,
helium for hundreds of thousands of years, carbon for a few hundred years, and silicon for just a few days. The process accelerates because each stage releases less energy per reaction as you approach the peak of the curve. And then it stops. Iron sits at the peak. You cannot release energy by fusing iron. There is nowhere higher on the curve to go. When the star builds an iron core, fusion ceases. The core loses its energy source. Gravity, which has been held at bay by the outward pressure of fusion energy for millions of years, suddenly wins. The core collapses in on itself in less than a second. The outer layers of the star come crashing down, hit the incompressible core, and bounce outward in a catastrophic explosion, a supernova. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of suns. The supernova explosion is so energetic that it can fuse elements heavier than iron. Gold, silver, platinum, uranium, all the elements heavier than iron are forged in the extreme conditions of supernovae and neutron star collisions. These elements cannot be produced by ordinary stellar fusion because creating them requires energy input rather than energy release. Only the extreme energy available in a supernova or a neutron star merger can drive these reactions. Every atom of gold in every ring, every necklace, every bar in every vault was forged in the death of a star or the collision of two stellar corpses. The nucleus governs not just the life of stars, but their deaths, and the creation of every heavy element in existence. And what remains after the supernova? In many cases, the collapsing core does not stop at nuclear density. It keeps going. Gravity crushes the core so intensely that the electrons are forced into the protons, converting them all into neutrons through a process similar to beta decay. The result is a neutron star, an object about 20 kilometers across, roughly the size of a city, containing 1 to 2 times the mass of the Sun. A neutron star is essentially one enormous nucleus. It is nuclear matter pushed to its ultimate extreme. The density of a neutron star is staggering. A teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. The surface gravity is about 200 billion times Earth's gravity. If you dropped an object from a height of 1 meter above a neutron star surface, it would hit the surface traveling at roughly 7 million kilometers per hour. These are numbers that sound invented, but they are the straightforward consequences of packing 1 to 2 solar masses into a sphere the size of a small city. The structure of a neutron star reads like a cross-section of nuclear physics pushed to breaking point. The outermost layer is a thin atmosphere, perhaps only a few centimeters thick, made of ordinary atoms, hydrogen, helium, carbon, compressed to extraordinary densities by the intense gravity. Beneath that is the outer crust, a lattice of nuclei arranged in a crystalline structure, similar in some ways to the atomic lattice in a metal, but under pressures that would crush any terrestrial material. The nuclei in this crust are ordinary nuclei, iron, nickel, and heavier elements, but they are squeezed together far more tightly than in any earthly substance. Deeper in, the inner crust, the situation becomes exotic. The pressure is so great that neutrons begin to leak out of the nuclei. They drip free, forming a neutron gas that fills the spaces between the remaining nuclear clusters. This is called the neutron drip regime, and it has no analogue anywhere else in the universe. You have nuclei sitting in a sea of free neutrons. The neutrons are not bound inside the nuclei anymore. They are loose, filling the lattice like a fluid between solid islands. Go deeper still, and the nuclear clusters dissolve entirely. The distinction between individual nuclei disappears. You enter the outer core, which is a uniform fluid of neutrons, with a small admixture of protons, electrons, and neutrinos. This is pure nuclear matter, the same stuff that makes up individual nuclei, but now forming a continuous fluid stretching across kilometers. The density here is comparable to the density inside an ordinary nucleus, about 230 million metric tons per cubic centimeter. The entire outer core is one vast, continuous quantum liquid of nucleons. And at the very center, in the inner core, our understanding reaches its limits. The density exceeds normal nuclear density by factors of 2 or 3, or perhaps more. At these extreme densities, the nucleons themselves may begin to overlap. The quarks inside neighboring neutrons may start to interact directly, no longer confined to individual nucleons. The matter may transition into a quark-gluon plasma, a state where quarks roam freely over distances larger than a single nucleon, no longer bound into protons or neutrons at all. Or strange quarks, a heavier variety not found in ordinary matter, may appear spontaneously, creating a new form of matter called strange quark matter that has never been observed in any laboratory on Earth.
Nobody knows for certain what the inner core of a neutron star contains. Our theoretical tools strain at these densities. QCD, the theory that governs quarks and gluons, becomes extraordinarily difficult to calculate at the densities and temperatures found in neutron star cores. Particle accelerators can create quark-gluon plasma at very high temperatures, and they have done so at facilities like the relativistic Heavy Ion Collider and the Large Hadron Collider. But the conditions in those experiments are hot and short-lived, while neutron star cores are relatively cold and permanent. Different regions of the QCD phase diagram, different physics may apply. Neutron stars are natural laboratories for nuclear physics under conditions we could never replicate on Earth. Every gravitational wave detected from a neutron-star merger, every precise measurement of a neutron star's mass or radius, gives physicists new clues about how nuclear matter behaves when pushed to its absolute extreme. The Indian-American astrophysicist Chandrasekhar calculated that white dwarf stars above roughly 1.4 times the Sun's mass cannot support themselves against gravitational collapse. His breakthrough opened the door to understanding all stellar remnants and their mass limits. Building on that foundation, later physicists showed that neutron stars face a similar ceiling. If the mass exceeds roughly 2 to 2.5 times the Sun's mass, even the repulsive core of the nuclear force, even the Pauli exclusion principle acting on neutrons, cannot resist gravity. The star collapses further into a black hole. The nuclear force, for all its staggering power, meets something it cannot defeat. Gravity, amplified by enough concentrated mass, wins. The nucleons themselves are crushed out of existence. Matter, as we understand it, ceases to be. Let us step back now and take in the full picture. Because the story of the atomic nucleus is not just a story about physics, it is the story of why anything exists at all. Start at the smallest scale. Quarks, bound by gluons through the fundamental color force, form protons and neutrons. The binding is so powerful that it accounts for most of the mass of these particles. The quarks themselves are nearly massless. Most of the proton's mass comes not from its quarks, but from the energy of the gluon field binding them together. Mass is mostly binding energy. The stuff you are made of is mostly the energy of confinement. Move up one level. Protons and neutrons, bound by the residual strong interaction, form nuclei. This force, a shadow of the color force leaking between nucleons, overpowers electromagnetic repulsion at nuclear distances. The specific balance between attraction and repulsion determines which nuclei are stable, which are radioactive, and how much energy can be extracted from nuclear reactions. This balance dictates the structure of the periodic table. It determines which elements can exist. Move up another level. Nuclei, surrounded by electrons held by the electromagnetic force, form atoms. Atoms combine into molecules.
Molecules form compounds. Compounds form minerals, water, air, organic matter. Chemistry is possible because stable nuclei exist. Every chemical bond, every protein folding, every strand of DNA relies on the existence of stable atomic nuclei. Without nuclear stability, there are no atoms heavier than hydrogen, no chemistry, no biology, no life. Move to the cosmic scale. Nuclear fusion powers stars, lighting up the universe and forging elements in stellar cores. Supernovae scatter those elements into space. New stars and planets form from the enriched debris. On at least one planet, orbiting an ordinary star in an ordinary galaxy, the chemistry made possible by nuclear stability produced something extraordinary. Life, consciousness, beings capable of looking inward at the very nuclei that make their existence possible.
The nucleus is smaller than a trillionth of a millimeter. You will never see one. You will never touch one in any meaningful sense. And yet it governs everything. The identity of every element, the energy of every star, the stability of every atom in your body, the light that crosses space from distant suns, the heat that warms planets, the heavy elements that form rocky worlds. All of it traces back to that tiny, dense, impossibly resilient structure sitting at the center of every atom. It holds together because a force of staggering power, operating over a distance shorter than the diameter of the particles it binds, can overpower the electromagnetic repulsion between protons. It holds together because neutrons add binding without adding repulsion. It holds together because quantum mechanics arranges nucleons into energy shells, creating islands of special stability at the magic numbers. It holds together because the laws of physics, the specific values of the fundamental constants, happen to permit a balance between the strong force and electromagnetism that allows complex nuclei to exist. Change those constants by a few percent and the balance fails. Nuclei fall apart or never form. Stars cannot ignite. Heavy elements do not exist. Chemistry stops before it starts. The universe remains a thin, cold soup of lone protons and electrons forever. But the constants are what they are. The forces balance as they do. And so nuclei form. Elements exist. Stars burn. Planets coalesce. And on a small, rocky world orbiting one ordinary star among hundreds of billions, beings made of atoms held together by nuclear forces look up at the night sky and wonder how it all works. The answer is sitting inside every atom of their bodies, a speck of matter smaller than anything they will ever see, holding together against every reason it should not, making everything possible by the simple, extraordinary fact that it does not fly apart.